Tagadan 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 pam pam tagadan 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 pam pam tagadan 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 pam pam tagadan.
Up next from CSCS is Giuseppe Loray, who will be talking Ceph, Cloud Native Data Workflows for HPC. Hey, Giuseppe, how are you?
Hi, fine. Thank you for letting me talk with this this afternoon. So my talk is about how storage at CSCS is evolving now with Alps, basically, with a focus on Ceph, which is something we started to have since 1 year. Okay, I will not spend time on what is TSCS and what is Alps, because you already heard a lot from Sadaf, and I think it is not worth to repeat. So, what is the storage at TSCS? I will try to say what is today and yesterday, and what is going to be today and tomorrow. Today is largely based on file systems. So we have a classic approach where we have a group of file systems providing scratch space for computing systems. And then we have another group of file systems which are dedicated to holding persistent data. In addition to that, we have also already since a few years a not small Dcache installation for LHC grid data, right? Plus, so these are kind of less general purpose, is more dedicated to a customer, and then there is a OpenStack based object store, a Swift object store. Also, that one is kind of address some specific project like Human Brain and Marvel, which is a material science project. Plus our tape library infrastructure, which is used to cover backup, archive, and HSM for one of our file systems. Since some time, we started to evolve our infrastructure in the, let's say, Alps context. So we added an additional cluster-based file system, which is being used already today as a scratch space for Alps. There is a lot of work going on about the evolution of this part of the infrastructures, which is will probably grow and absorb workloads from which are currently done with the in different ways, but yeah, this is really work in progress. Probably it's too early to keep details. Another new component is Ceph. So we have installed a Ceph cluster last year, which provide both HDD and NVMe space, let's say, which is the component which allows us to implement more cloud native workflows in the context of Alps. So I will give some information about what is Ceph in case there is anybody not really aware of the tool. It's a storage system which provides in a single system several interfaces. So it provides object, block, and file storage in a single system. It is designed from the scratch to run on commodity hardware. So basically servers with internal disks. The backend, the actual backend which managed hardware and data management operations is called Radus. And so Radus takes care of disks, of data replication or Azure coding computation, scrubbing, rebalancing, etc. And whatever is the way you write files or S3 objects or device block device, sorry. What you do, you are using an interface which at the end ends to write the data into Radus as objects. So Radus is an object store. So everything you write at the end, it will be an object. Ceph objects are stored in pools. A pool is a logical partition of the storage capacity, and you can have multiple pools, can use different pools for different data. So there is a lot of freedom there. There are two types of pool, in particular respect to the data resiliency. The first one is the replicated pool, where data are basically the objects are replicated. The default way is 3-way replica, so that you can tolerate. If you have 3 replicas, you can tolerate 2 failures, disks or entire servers at the same time. So this is the initial way Ceph has started to offer space, and is not very efficient from the point of view of the capacity, but it is very light from the CPU perspective. Since few years, it is possible to use erasure coded pools, where basically you don't replicate, but you can calculate checksum. So when you write an object, this is striped in M data chunks plus K code chunks. Typical values are 4 and 2, or 8 and 3. There is a lot of freedom there, and you need to find the best working point for your cluster. With erasure code, you can basically tolerate the number of code chunks failures. So if you have 3 chunks for the erasure code, you can tolerate up to 3 concurrent disk failures, or even entire service failures. The good point about erasure coded pools is that it is much more efficient from the capacity usage perspective. It uses more CPU. Sometimes could be not an advantage. As I said, there are 3 different interfaces to the same cluster. The one is Radus Gateway, which implements basically a RESTful gateway, which provides access through the Amazon S3 API and OpenStack Swift API. The S3 functionality coverage is very wide, is very good. It provides multi-site functionalities. It is very, let's say, comfortable in a multi-tenancy environment. It provides some self-management capabilities for buckets, like the user can decide on his own how to expire the object. If want to set advanced ICLs is possible. Also data migration between buckets or between what are called storage classes are possible. So it's very advanced. And all the available S3 clients are working fine with the S3 implementation of Ceph. The second interface is the block device called RBD. Application receive a block device from Ceph in this case. This is widely used for OpenStack environments as a Cinder virtual volumes backend, and also in Kubernetes environment where you can back Kubernetes persistent volumes with the RBD. Most of the today's Linux kernels or includes the RBD driver, so you have a kernel space support for this. And there are a lot of nice features like team provisioning to optimize your capacity usage, snapshot exclusive locking to avoid the corruption of devices if you try to access from different points, and the live migrations, so you can move your volumes live between pools. The third one is the CephFS. This is a POSIX file system. Actually, I think is the first one to be implemented in Ceph. The first one, and then RBD and Radus Gateway came after. It is highly available because you can run multiple MEDS services. Allows to separate data and metadata, so this can help the performance. There are no gateway bottlenecks. Once you mount the file system, your client talks directly to the data servers. So there is no, there is some possibility of scaling there in the architectures, which is really, really nice. Important features are, of course, snapshots. You can use extended attributes to decide how to stripe, this is the layout, how to stripe your data, or how to place your data, meaning in which pool, in which Ceph pool you want to place your data, meaning you just setting certain extended attributes on a directory, you can decide that you will send your files into a fast storage pool or traditional hard drive pools. This is also nice. And it has an authorization system, and this is true for also for RBD, which is based on secret keys. So this allows to kind of, it has to be very, very useful in a multi-tenancy situation. I will recall this later. So what we did in our implementation at CSCS, we bought a cluster. We didn't start small, actually. It's already a kind of medium-sized cluster, or maybe large, made of 20 OSD servers, which are the servers with disks, 36 hard drives of 60 terabytes each, plus 4 NVMe devices, each server with the double 100 gig Ethernet, plus 3 nodes which are called monitors, where the central Ceph services run to keep the state of the cluster, the performance monitoring, health monitoring, MDS, which it is for the CephFS metadata, Prometheus, Grafana, etc. In addition, we also dedicated 3 nodes, which currently are virtual machines, but in the next future will become bare metal nodes, to run Rados Gateway for the S3 interface. In this case, you have to run that workload on a separate group of machines. So as I said, we started last year, and we are going probably to double this year. We started before with the default replicated with replica 3 pools. As you know, we were still learning about Ceph and how to merge it. So that seemed to be the safest way to start. Now we are also using Azure coded pools, both for hard disks and NVMe devices, which we knew from the start it was good for capacity utilization because you waste much less space on redundancy. But we discovered that also the performance are enough for our cluster, for our sites are quite in general better than for replicated pools. So there might be exceptions which we are still kind of evaluating, but are also kind of corner cases. Like if we, in case of read-only streaming I/O, maybe the replicated pools in that case might show better performance, or the same could happen for workflow with very, very small files. And in this case, the overhead of CPU for the Azure code computation could play a role. But these are corner cases, and we are still kind of evaluating these things. We did some benchmark to decide how to configure these pools. The first kind of benchmark is meant to understand whether it was more convenient to use replicated or Azure coded pools with hard drives. We used a tool which is included in Ceph, which is Rados Bench, which does I/O at the Rados level, so not through any of the 3 interfaces I described before, but directly talking to the Rados layer, so reading and writing objects. We did 2 kind of measurements, write only or read only sequential I/O, just to see where we could peak basically with the performance. And we did also write mixed to read. So we were measuring write performance, but at the same time we were doing also read activity at the same on the contrary, because this is a kind of mixed approach where seems to be more realistic. We have a shared cluster, a single shared cluster, where at any given time there will be always different kind of activities. So these are the ones which you consider most meaningful for our decisions. So we run this benchmark for different kind of pools replicated with the replica tree, and then different configuration for the registry coded pools. And we found that basically the main result is that for hard drives, the pool which is performing better for mixed workload is the one with the 4 data chunk and 2 code chunks. And so this is what we decided to use for production. The same kind of a comparison has been done for NVMe devices. Same kind of benchmark, same tools, same kind of logic. And in this case, we found that with the NVMEs, results were kind of very similar between the registry coded pool with 4 data chunks and 2 code chunks, and the one with the 8 data chunks and 3 code chunks. In this case, we decided to use the latter one because it is more advantageous for capacity utilization. So there is less waste of space using this one. So this is what we decided to use for our pools with the NVMEs. Another aspect which we had to understand kind of how to configure was the number of placement group. Placement group is a space unit which is used for internal operation like rebalancing and scrubbing. When there is a server down or a disk down, Ceph will kind of really recreate the content of those disks into a different server. So this is the rebalancing. This kind of operation is not done object by object. It would not scale. So objects live inside a placement group, and the entire placement group is considered and is moved or copied or rebalanced in different servers. When you create a pool, you need to specify how many placement groups you want this pool to use. And so that's why we try to understand with the measurement of the throughput versus the number of placement groups of a pool. And we found that a reasonable result in terms of throughput is achieved with 1024 placement groups. So this is something we use to set up the pools as well. Another parameters which we had to kind of measure was how the throughput would grow or not grow with the number of clients. So how many, on the other way, how many clients do we really need to be active on the Ceph cluster in order to provide the maximum performance? And this, we saw that is happening with about 50 clients, which is a kind of easily reachable working point with the current CSCS sites. So that's all for the benchmarks and how we decide how to configure the Ceph storage. Now I would like to show why we are using Ceph and how we intend to use, or we are already today using it. There is some use cases. The first one is very generic, is as backend for Kubernetes persistent volumes. We have different Kubernetes clusters at CSCS with different functions already. Probably there will be more in the future with ALPS. In Kubernetes, we have a so-called CSI, which means container storage infrastructure. It's a standard which defines how a Kubernetes cluster could connect to external storage providers. We are using on our Kubernetes clusters the CSI plugins for Ceph RBD and Ceph FS to provide persistent volumes. A more specific example is the WLCG, so the computing and data workload, which comes from the LHC computing grid. And we are running this for several years, and we have found historically issues sometimes when this workload is run against traditional HPC file system like GPFS or Lustre. It's very often for metadata operations in particular, I believe. So what we are trying to do, and this is something ongoing, we started to test, but this is not yet full in production, is still in evaluation. We are trying to provide NVMe backed Ceph RBD volumes to computer nodes. In the computer nodes, this device is used to create a local file system, and a local directory on this file system is used to run the scratch space and to run the computing. And this should have the advantage to reduce or completely eliminate the metadata traffic from the computer node to an external shared file system, because all the file system work would be done locally. So this is the first use case we are investigating. The second one is still about persistent volumes for Kubernetes, and still actually for the WLCG workload, it is about Dcache. We have Dcache running at CSCS since years, with the classical setup on bare metal, with in our case a GPFS file system as a backend. Last year we started to move the Dcache pools, which are the service actually providing data to users, from bare metal nodes to Kubernetes pods, and providing these pods with RBD volumes, where there is a file system local to the pod. This is working since 1 year, and it is a kind of successful in the sense that I believe users didn't realize too much about this change, so this is already a success. And the spirit is a bit of consolidating the installation of the cache from a dedicated cluster to a shared one in Kubernetes, give more flexibility, and treat the cache as well as infrastructure as a code tool. At least run it on this kind of environment. We are still in the process of migrating from the previous step to this new one, but this is already something which is being used and is, I would say, working. Another use case we are considering, this is not yet reality, but next future we will try to evaluate and to test this scenario, is using CephFS as a home directory backend. As already has been explained, in Alps we will have, and we have already today, a multi-tenancy approach where multiple clients will have a different environment with a certain degree of isolation. And this is not very easy and sometimes inside the tenant, the customer will have also super user power, so they self-manage, so they have a kind of a root power. And this scenario is not really easy to serve with the traditional file systems like GPFS, for example, where if you want to mount a file system to a cluster client, the client on the other side, they basically get all the file system. There is no way to expose a part of a subtree of the file system. You can use root squash, you can play with the UID, JID, but this really doesn't work completely. On the contrary, CephFS allows to limit the export amount of the file system to a subtree. And the authorization used to do this is using a secret key instead of IP or host names or UID. So you provide the secret key to your client cluster, and they will be able to be root if on their cluster, if on their tenant, if they want, and still mount the file system and mount and access only that part of the file system which they are meant to be. So this is something for sure which is going to be tested in the next future. the last use case, which I will describe in a very, very generic way, because as of today, I cannot kind of details which particular customer and any details about this. But we have already something running, and which is proving to be kind of a solid approach. So we have kind of ingestion distribution pipelines where applications running Kubernetes loads data from an external source, typically is an external S3 endpoints, process this data inside Alps infrastructure, and store this data on our S3 backend on Ceph. And after that, this data are again made available to external consumers for further processing. And this is all about Ceph I had prepared. So thank you for your attention. If you have any question, I would be happy to answer.
Giuseppe, we do have one question from Adam. He says, for PGs, did you try with the autoscaler enabled?
Yes, actually, this is what you get by default in the release we installed, Octopus. And actually, we are disabling autoscaling because the strange behavior we get when we create a pool at the beginning is that the first time that autoscaling does is scaling down the PGs. While we know that under a certain number of PGs, the performance are not good. So for the moment, we are not using that. I know that with the next release in Pacific, this has been changed, so it will be easier to use autoscaling.
Okay, thank you. That's the only question I have in the queue.
Yeah, Brian, I have one comment for Giuseppe, maybe, if you allow me. Giuseppe, could you tell us a little bit about the backup process in Kubernetes?
Well, I didn't include for the moment much about backup because there is a lot of in brainstorming now. The fact is that there is a very little, let's say, in general for Ceph, there is very little as a backup. And very, very little as backup to tape in general. So we are trying to approach this from different angles, depending on the kind of data. For example, for Kubernetes persistent volumes, we started to use Velero, which is an open source product. Velero, okay, it's free, it's open, which is good. It's not very easy to make it work as we want, because we want to use Velero in combination with the Ceph snapshots. So you want to get a snapshot on a volume before you do the backup, otherwise the result would be not really useful. And this is done. We are testing this in kind of same production. It's already done. What we miss is to make such that these snapshots are copied to an external repository. So basically to tape, if possible. And this is something still we are working on. For S3, we started an investigation about using the multi-site functionality of Ceph, and using as an additional, let's say, component of Ceph site an external S3 endpoint, where this S3 endpoint is provided by a tape-backed piece of storage. This is also kind of in test now, and we are trying to fix some technical issue. But basically, the bottom line is that Ceph is able to provide the replication for S3 data, and you can define one endpoint for this application, which has actually behind tapes. This is the idea. The last point is, yes, is CephFS. And for CephFS, we have kind of different plans. For now, we are using CephFS only as a backend today as a backend for persistent volumes for Kubernetes. So this is already covered by Velero. In the future, we might, as I said, we might have to put home directories on CFFS, so a backup there is needed. Then we have the choice to use our current backup solution, or there are also other possibilities, but this is kind of planning still.
Thank you.
You're welcome.
Thank you, Giuseppe. Appreciate the presentation.
Thank you, Matt.
Brian, before changing topic, there was a question I answered while it was going from Joseph Paretti. I'm not sure if everything I wrote is clear because he was asking about multi-tenancy and OpenStack on the Swiss supercomputer. Just to make it clear, the Swiss supercomputer is not having OpenStack, is using or is going to use Ceph, but not the OpenStack layer. Ceph as a backend storage, a software-defined storage. The OpenStack we have at CSCS is a different platform, and at this stage is not even connected to this Ceph. And for the multi-tenancy in the supercomputer, we are intending to go Shasta way, so more using Kubernetes too. And I don't know if someone wants more information, just ping me offline. I will give.
Thank you, Stefano, for the clarification.
Tiga-dum, pam, pam, tiga-dum, 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 pam, pam, tiga-dum, 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 pam, pam, tiga-dum.